Hello there and welcome to this course on machine learning for healthcare with Python. My name is Valentine and I'll be your instructor. In this course, we're going to start by learning about the learning outcomes. After that, we'll get to talk about the important concepts in relation to machine learning for healthcare with Python. We're also going to learn about why we would want to learn about those concepts, how they help various stakeholders within the healthcare industry. After that, we'll get to go through a practice session that will entail putting into practice what we will have learned theoretically using the Python programming language. And then later, we'll talk about the next steps. So what comes after having gone through this learning experience. So let's get started. By the end of today, we are expected to have achieved these learning outcomes. We should be able to describe the foundational concepts of machine learning in healthcare and being able to distinguish between what is supervised and unsupervised learning. These are just two different categories when it comes to learning about machine learning. We should be able to explain the process of data preparation for ensuring that we are able to create what are called machine learning models that answer our research questions appropriately. So in that process of data preparation, we are going to learn about just concepts like data cleaning and being able to normalize our data set, as well as perform feature engineering techniques. So it might involve being able to derive new features or new pieces of information or new columns from existing columns of data. We should also be able to demonstrate proficiency in implementing various machine learning algorithms. So there are quite a number of them, and some of which will include decision trees as well as support vector machines. Lastly, we should be able to make predictions and give recommendations based on those machine learning models that we'll have trained. And the idea is that we would be in a position to support clinical decision making and improve patient outcomes in healthcare settings. So those are learning outcomes. By the end of this learning experience, we should be in a position to say that we have achieved these learning outcomes. Starting off, what is machine learning? So you can think of machine learning as a process that involves using what are called algorithms and statistical models to be able to create these special programs that are able to learn from historical data and make new predictions and make predictions based off that process of learning, which is usually referred to as training. So generally, what maybe if I explain in a layman's terms, machine learning generally involves you would create these special computer programs called models, and then these models you would train them off historical data. It could be patient data, it could be hospital data or pharmaceutical data, and then once those models of special computer programs have learned from that historical data, they can then make predictions. And for example, you might have a program that is able to predict whether a patient will be readmitted to a hospital based on some information that you have had about patients in the past. So yes, you have this new patient with a set of data set that's quite relative, that's new, could be demographics data plus a few information related to their illness. Then you could decide to train that machine learning model that you're going to make a prediction for whether that patient will be readmitted or not. You could train that model based off historical data of other patients. It could be thousands of patients, so that you are able to effectively make that predictions, taking into account of all the different pieces of data that you've had about those historical or those patients in the past. So the process of machine learning just entails being able to create those special programs. And we can do that through the use of many tools. And one of the most popular tool is Python. Python is a programming language that we can use to create those models. And we can use Python for many specific projects, and a few include being able to create what are called data pipelines. So those are just programs that collect data from different sources and they aggregate it together in a format that can be used by various stakeholders. We can also use Python for creating visualizations or for creating data sets that are clean for further analysis, such as now what we're going to be working on, which is creating machine learning models. We can use Python for creating dashboards and a whole lots of other tasks. But Python is primarily known for having an ecosystem that's quite mature when it comes to performing machine learning, and that's why we're going to be learning how to use it. So we'll implement various machine learning algorithms. By the way, there's a difference between an algorithm and a model. An algorithm, you can think of it as a mathematical function or some sort of code that has been written that you can use to now create a model. A model is that other new special program that's now that you now train on historical data. So you can think of an algorithm. By the way, an algorithm in computer science, it's usually just a set of instructions that perform a specific task. So you can think of a machine learning algorithm as a complex mathematical function that works differently. There are different algorithms and specifically machine learning algorithms that all work differently, and you can use one that works in a specific way to be able to train it on some historical data that we call a training set, but we'll get to explain a bit more in a few. And then use that model, which is the final product, to make new predictions. Maybe in that case of whether a patient will be readmitted or not, you can have maybe 20 new patients, but you would use that model that you've created to predict whether those 10 or 20 new patients will actually be readmitted or not, without necessarily requiring to go again patient by patient and analyzing that data. So the model itself does that particular work. So for example, another use case would be you could be a data scientist specialized in healthcare data analytics, and you can create a predictive model to analyze patient data and identify individuals at high risk of developing diabetes. So the variable of interest would be whether or not a patient has a high risk of developing diabetes, and you could have historical data based on other patients' data that you've collected that have already had high risk of have already developed diabetes, and others haven't developed diabetes, and you can use that data to train on the model and use that model later onwards to just make newer predictions, just saving time and resources and generally ensuring that organizations are able to solve for problems. There's so many problems in healthcare we can work towards when it comes to machine learning, and that's what we're going to uncover. So let's continue just learning a few more things. So actually this should read why machine learning, machine learning for healthcare with Python. One of the things, there are many reasons why I would want to perform machine learning for healthcare with Python. One of it being able to maybe predict diseases at an early stage. If you have, again, historical data on patients' data who have developed and those who haven't developed those diseases, you can use a model to be able to predict whether newer patients or newer subjects at hand are likely to develop those diseases. It could be you are a public health specialist and you're looking at data in relation to various diseases, and that would allow you to, as you've made those predictions, that would allow you to be able to provide recommendations to other stakeholders, like maybe policymakers, who would provide timely interventions, and even just allocate resources for maybe medicine or for other interventions that would come in handy to ensure that those diseases are able to be taken care of. You can also use the models that you're going to create to analyze patient data, so that you're able to tailor treatments and medications for just the individual patients, rather than having maybe treatments which are just a bit more broader, and you're able to specifically tailor treatments for just specific patient, depending on the kinds of symptoms and other data and other factors at hand. You could also use machine learning models to predict patient admissions. We've elaborated an example, or admissions, and also resource needs. Just in case if you have many hospitals data and you'd want to maybe predict something about that, then you can use machine learning to do that. We'll talk about another specific use case still with regards to hospital data in a few. Predictive models can also help us identify high-risk patients for targeted interventions, which of course would reduce costly hospitalizations and also emergency room visits. Those are just a few reasons, but just a few more, just to give you a good idea of the kinds of problems that we might end up working on. Again, problems in healthcare pertaining to machine learning are quite vast, and it's up to you as an expert to determine whether a problem is a problem that can be solved using machine learning concepts. So, and a few examples, of problems that you might solve using machine learning models would be predict whether a patient has diabetes based on their medical history and biometric data, predict the risk of heart disease for patient based on their lifestyle factors and medical history, predict the length of a patient's hospital stay based on their admission data and clinical condition. Given historical data, predict equipment failure to schedule timely maintenance. Given demographic and environmental factors, predict areas at higher risk for certain diseases, and detect anomalies in healthcare claims data indicative of fraud and abuse. So these are just a few examples that should give you just a good idea of the problems that you might end up working on if you and using machine learning if you are in the healthcare industry already. A few other concepts to keep in mind before now going a bit more deeper on into practice with Python in relation to machine learning would be whenever it comes to learning about machine learning, there are various types of problems that you can work with. There are two categories of machine learning, and you can think of them as one called supervised learning, and there's another one called unsupervised learning. In supervised learning, we would train a model, and then later onwards, we would have it make some sort of predictions. We would train a model, test its performance, then use if it's satisfactory, if it performs well, then we can use it to make new predictions. In unsupervised learning, we do not train a model. So in unsupervised learning, we just give a model data and we tell it to do a particular task. So for example, we might want to tell it just discover categories, or group all the records that we have given you in this, group all the records in this data set into various categories. So that's where unsupervised learning would come into play. So supervised learning involves training, unsupervised learning does not involve training. Now, for both types of learning, or both categories of machine learning, by the way, these are just the basic ones. There are other two types, which I won't mention in this workshop. I won't go deeper into, but I'll mention for just awareness, but not really go deeper into. There is semi-supervised, which involves a blend of the two, supervised and unsupervised learning. And there's also what is called reinforcement learning. These are just other types of machine learning, but the most common types of machine learning categories that are applicable in industry include just supervised learning and unsupervised learning, but a lot usually of problems are classified as supervised learning. However, you will also get to work on unsupervised learning. On the other side, semi-supervised reinforcement learning, that is something that you might end up working on maybe in rarest of circumstances. Not all organizations have the needs of those types of learning, but you could always explore that further. In these two types of learning, supervised and unsupervised learning, we work with data sets, historical data sets that we would want to use for analysis. So, for example, for supervised learning, we would want to use a historical data to train a model that we then use for making predictions. In unsupervised learning, we just give that data set, that historical data set that we might have, we actually need that data set, we give it to a model, and it just gives us, it could give us categories. In some other situations, we might end up still as part of unsupervised learning, rather than giving us categories, we might want to represent the data set, have a different representation of the original historical data set that's a bit more compact, and that's usually what is referred to as dimensionality reduction. But unsupervised learning, we just do not train a model. But both we have data sets. In both, there's also in those data sets, we usually also have what is called features. These are from high school knowledge, called just independent variables. These are the variables that you would have, and you would have, they're usually called independent variables, and there's the dependent variables. These are the variables that I think, if you might remember, you can be able to collect about maybe patients. So, for example, in unsupervised learning, you might have, let's say, let me see if I can give you an example of unsupervised learning, which I'll get to explain a bit. So don't worry about even the title of this particular case. Let me see if I can be able to share. Yeah, so we might have this date that's a bit too, yes, this one. Age, gender, cholesterol level, blood pressure, smoking status, exercise habits. So in this particular situation, we might have this data set that's in relation to supervised learning. And the idea is that you would have what are called features. Features are the variables that are called age, gender, cholesterol, blood pressure, smoking status, and exercise habits. So we are going to be giving our model information, actually the data in relation to these variables, and we are actually going to ask our model to predict the heart disease column. So in supervised learning, we have independent variables, and also we have a dependent variable. In data science, data analytics, we don't use independent variable as a term. We also don't use the dependent variable as a term. But again, in different contexts, you might want to use them, especially in mathematics. But in data science, we would normally term them as features. Like the independent variables are the features, and the target variable, or the dependent variable, is what is called the target variable. In some situations, you might hear it go by the name label. So the target variable, the dependent variable, can also be called a label. So in supervised learning, we normally have a data set that has both dependent and independent variables, or both features and the target variable. So in supervised learning, we have a full data set with the features and the dependent variable, and the target variable. In unsupervised learning, we do not have the label. We do not have the target. We do not have that dependent variable. So in our case, for example, here, this is unsupervised. Here we don't have, we have this data set that you can see here, but we don't have a variable that we are trying to predict. We don't have that data. And in unsupervised learning, that's where we are trying to predict. We are telling this model, learn from the observations within the data and predict a new column should be just a group. We want to cluster or to assign each and every record a certain group. So generally, in unsupervised learning, especially in one type of unsupervised learning that's called clustering, what we want to do is to group all the records together. It's generally to group, like to assign each group, each record a group that characterizes it. So generally, it's like we have 100 records. We might want to group those records into different categories, into different buckets. And that's where clustering, or which is part of unsupervised, will come in. So the idea of features will be in both types of categories of machine learning. So there's unsupervised learning and supervised learning. In unsupervised learning, we don't have a target variable, we don't have a label. So that's why we say unsupervised learning, it's a machine learning paradigm or type of machine learning that involves having a model that learns from unlabeled data sets. So there's no label, there's no target variable or dependent variable, and it identifies hidden structures or relationships without just generally guidance. And there's different types of unsupervised learning. There's k-means clustering, which now involves being able to assign the records within our data set to different categories. And there's dimensionality reduction, which just generally involves reducing the number of columns within your data set into what are called components, which are just representative columns of the original columns that were there. So sometimes you might want to perform dimensionality reduction to reduce the data set size, and then use that new data set for machine learning in some cases. And that might even end up improving the performance of our model. But yeah, that is something, it's an advanced concept that one can also cover in a separate workshop. But our focus will be just to learn generally how to work with the two types of supervised learning as well as unsupervised learning. We will talk about, we actually go through k-means clustering, and in supervised learning we'll also cover methods such as regression and classification, analysis methods. So yeah, I hope that made a bit of some clarification. In supervised learning, we have two types of methods in supervised learning. So I'm sort of going deeper and drilling it a bit. You can even think of it as a tree. So you have machine learning at the top. On the left branch, you have supervised, and the right branch, you have unsupervised. So on the left branch, where you have supervised, you have regression, another branch, and sub-branch, another one called classification. So supervised learning involves what is called regression and classification, and regression involves being able to make prediction for a numerical variable, while classification involves being able to make some prediction of a categorical variable. So for regression, we would be talking about say, for instance, we would want to predict the length of hospital stay for a patient admitted with pneumonia. The data set that we would have these variables, would have vital signs on admissions, would have laboratory test results, maybe comorbidities or commodities, age and smoking status. We might want to maybe predict some sort of numerical variable. And maybe if I can just go a bit and display that data set. Assuming this is our data set, it may not be that clear, but you can always just increase your screen size. We have vital signs, temperature, heart rate, blood pressure, respiratory information, lab test 1, lab test 2, comorbidities, and age, smoking status. So what we have here would be our features, and our target would be the length of stay. So we would create a model that we train on historical data of other patients who we have data about, and the idea is to determine the length of stay and then we can be able to do that. For hospital, there are many reasons maybe they might want to do that, so that maybe they ensure that the resources that they have are allocated maybe, or efficiently. Maybe it's to get more staff or reduce staff numbers, etc., especially with big hospitals. So yeah, so that's a regression problem. So we are predicting a numerical variable. For classification, we're usually predicting a variable that is categorical in nature. It has two values. So for classification, you could have, these are the features: age, gender, cholesterol level, blood pressure, smoking status, exercise habits. But this is the target, but it only has two types of values. There's 1 and 0s. One would describe that this patient had heart disease, this patient had also heart disease, this other patient did not have heart disease, etc. So regression, numerical variables would be the ones we would be predicting. For classification, we would be predicting a categorical variable. Now, an example of a question in relation to classification would be: predict the likelihood of a patient developing heart disease within the next 10 years. So it would be either yes, this patient will develop, or no, this patient will not develop. But you can still go further and get those probability values using some machine learning models, because all models work differently, but some of them will just be able to give you the actual probability value. So yeah, that's between 0 to 1. Yeah, so those are just general concepts that you need to understand in relation to class regression and classification. In unsupervised learning, there's clustering. So a question that we might end up working on would be: can we cluster hospitals based on patient demographics and healthcare utilization patterns, so that we're able to allocate resources more effectively? You might have data as shown. So the data set might look like this. You have hospital ID, but hospital ID may not necessarily be of that importance. We might as well just not work with that data. You might have hospital size, medium age, percentage female, and admission rate, and mean length of stay. So our goal here in unsupervised learning, more specifically for clustering, where we would want to cluster these hospitals into different groups. Maybe they're hospitals which are in high need of resources as opposed to others, and then we can just study the different groups much more closely, because there are patterns which actually bring those hospitals together. Generally, when it comes to supervised learning, we would perform these steps. First, load data, clean data, split and train the data. So we would split our data into features, and then features, and also a target. Then later we would also move towards splitting into what is called a test and a training data set, which we'll get to learn. Then we evaluate how the model performed in terms of the training process. Then we make predictions. In unsupervised learning, it's almost similar, where we do the same. We also do the first two steps, but in the third step, we do not split. We just train the model once we have cleaned the data. But we can also do what is called normalization or standardization, which just involves ensuring that all the columns or the column data is also within the same scale. So we also get to see how to do that. We evaluate how the model performed, or evaluate whether the model was actually the best one. Then we can use that new data set to make new predictions. Not new model to make new predictions. That model to make new predictions with maybe some pre-processed data that we have had. So yeah, that's it. That's it in terms of giving you a strong foundation of skills into machine learning. Now we're going to move on into our practice work. Sorry, it was that long. It took us a bit longer than expected. We're now moving into applying those concepts that we have worked with. In the description section of this video, just click on the link that we've shared. It takes you to the page that looks like what you're going to be seeing on your screen. It will take you to this page, machine learning with Python, actually with healthcare. We'll update that. once you, it has, let me even just update it. I will update it later. So what you'll need to do is to click on the sample practice resource, and that will take you to a notebook that looks like this. So this is what you're going to get, and that's what we are going to be using for this particular session. Yeah, so and if you're interested in learning a bit more deeper and getting more exercises as well as the solutions for the challenges that we are going to be working on, you can consider becoming an Afterwork member, and you'll actually get access to all the resources that we have on Afterwork. We have over 100 workshops that we've done so far, so you'll get resources to all those workshops, content on our website, and you can always get to learn a bit more. Like, for example, if you want to practice a bit more of machine learning work, then you can always just explore the resources, extra resources that will provide quizzes, readings, as well as projects, as well as solutions to those projects. So yeah, once you get to this page, the first thing that you need to do is to save a copy. I'll actually not use my sample notebook. I'll use the practice notebook. So for those who are Afterwork members, you can use the practice notebook. It's just similar to the sample notebook, only with the sample notebook, you don't have the challenges. So the first thing that you need to do, you can go to File, then Save a Copy in Drive, and a new tab will open with a copy of this notebook. And then you can use that one. You can close the old one, and you can rename it by clicking on the very top. So let's do that. Let's go File, then Save a Copy in Drive, and we'll open the other notebook that will open in a new tab. For me, I'll open mine in playground mode so that I don't apply any changes to my notebook, because it's a master copy, and I wouldn't want you to see the changes that I'm going to be making during this learning journey, because I mean, the notes will be used by everyone who actually gets to work on this particular workshop. So let's do that. It might take a few seconds before it loads. All right, so mine has loaded. What I'll need to do is to click on, close it here. All right, so once you've done that, the next thing that you need to do, still while you're using your sample notebook, I'm using a practice notebook, is to click on Connect at the very top right. You can even just zoom in a bit. So at the top right, you'll see Connect, so click on Connect. And we are going to be working on different problems and working towards just creating models that we can use for prediction. So starting off, we'll get to learn about classification. So we mentioned when it comes to classification, we are creating a machine learning model that we train on historical data. And that model, what it will do is it will predict a categorical variable, a variable that's not numerical or continuous in nature. Could have just different categories. So let's learn how to work towards that. There's an example as well as a challenge for that. So let's expand this classification. So this is the problem. How do different classification models perform in predicting whether a patient will have heart disease? So we will just import the necessary library that we will need. We'll import, for now, we will import those other ones later. So let's import pandas by clicking on this link over here. If you get a pop-up, just know that you did not save a copy of this notebook in Drive, and you can always just refer to that so that you're able to make changes. So once we have run that, it should see a check, then we should be good. The next thing that we need to do is to load and preview the data. So we can import the data set, which is here, and preview the data set again. So this is the data set that we are going to be working with: patient ID, age, gender, weight, height, blood pressure, cholesterol, diabetes. It has just quite a number of variables. But what we are interested in here, based on our research problem, is that we want to predict whether the patient will have heart disease. So this is our target variable, heart disease. Something else to note is that we need to ensure that we do away with the data that we don't need, and we also ensure that we prepare the data generally for just training. And machine learning models normally take numerical data. So for example, in our case here, Gender column has textual data. We would need to convert that. Blood pressure also has technically text data, because these are two values which have been separated by a left back forward slash, but now this is, I think this is a forward or backward slash, I'm not sure, but this character that you see here, this is also, we would also need to update the values for cholesterol, diabetes, smoke, and heart disease. By the way, all these ones, the text data that you see here, we would need to transform them. So by transforming, it would mean converting the text into the equivalent numerical format. And we will see that, how we can do that. But before we even do that, let's display just some statistical information for the numerical variables. So patient ID, we're not so much interested in that, but we're interested in age, weight, and height. That's what we're going to be working with in terms of the numerical data for that already exists within our data set. The reason why we even just did this, one of the things, just gives you just a good idea of how the data is. Like you can see that based on our maybe age, the count, we had 100 for age, weight, and height, and it just means generally there are no missing values, which is also something important, because some models would need for us to before training handle missing values. Otherwise you'd get errors. They cannot work with just missing values. If there's missing values, you can just impute them, and there's also a workshop on that if you want to visit and learn more about imputation. Our focus is not really so much on cleaning data, so we will I'll just explain the processes. I've tried as much as to use the most simplest techniques for just working with just pre-processing techniques. So for example, so once we have done that, we've just learned a few things. We now want to perform the data pre-processing techniques. Like we want to drop patient ID, we want to convert gender into a male, female, into numerical equivalence. We can split this column so that we have blood pressure values which are on the left in one column, and on the other, then we drop or we delete the original blood pressure. Cholesterol will also convert the text into numerical equivalent. The same case with diabetes, smoker, as well as heart disease. Even though it's also our target variable, we will also want it to have just its numerical equivalent, so that our model can also learn from that data. So starting off, gender, for the gender column, we replace male, all instances of male with a 0 and all instances with a 1. It's sometimes important. I already know initially that those are the values that we have in the data set, but sometimes it's important to even just identify the unique values for each and every column, but that is something you can do that later. But for ease of learning, just note that for the gender column, we have male and female. We don't have any other value. So we replace male with 0, female with 1. Cholesterol, which is this one, we replace it with, we replace normal with 0 and high values, instance of high with 1. Diabetes, we do the same thing here. Diabetes, instances of no with 0, instances of yes with 1. Smoker, instances of no with 0, in instances of yes with 1. Heart disease, this one that we have here, heart disease, instances of no with 0 and instances of yes with 1. By the way, we're using a map function which allows us to be able to do what is called encoding, or to do that replacement. You can use other different techniques. They're called encoding techniques that one could use. We won't cover details about them because it's an extensive. We could actually even have a separate workshop for that if the learning experience was that extensive. So we then move on to our blood pressure column. So what we want to do is to split the blood pressure column using this character. And we want to have those separate values. Initially, the blood pressure column is in a string format. So we use the split function, to split the values, that value into just 2 different values, and the ones that the value on the left will be stored in this new column called systolic DP, and the values on the right will be stored in diastolic BP. And then expand just means you just want to expand and split them separately, and then we convert both have those 2 columns as to have an integer data type for further processing, so that it has numerical values in nature. Then we delete now the old blood pressure column, which has these 2 values combined, and also we delete patient ID because we don't need it. We apply this to our original data frame. Those changes by saying in place to true. Now the change of dropping, so the deletion action will actually be applied to the original data frame or the original data set by setting this to true. This axis just equals to 1 just refers to the columns. You want to delete the columns. And then we also delete all the records with missing values. Again, here, this is for simplicity, for ease of explanation. Sometimes you would want to, first of all, to check whether those missing values are actually records that the records with the missing values are records we can do without. And if so, then we can just delete them. But some instances you would want to investigate further, then do some handling missing values technique. So let's run this to ensure that our data is correct. By the way, you can print the data that we have, data.head, to just preview it. I just created a new code cell and then printed data.head to just preview how now our data set looks. Now this is the data set that we can use to train. It has numerical data. So then we separate the features. So once we get this, we would need then to split and train the model. But as part of that process, we would first of all split the features and the test and the target variable. So we have what I have highlighted is what is the features. What are the features? And this is what not what I have highlighted. This is the feature data set. These are features, and also these 2 are features. And what we have here is our target variable. That's what we want, and we save them in these 2 variables. Capital X is and this is Y. So our features will be in X, and our target will be in Y. Then what do? We then decide to split again. Once we have a data set that has features and another one has target. The next thing is still part of this process of training a model, splitting and training a model. We are going to say that we want 80 records for both training and test for the original data sets for these 2 records. So we have the X and Y tests, but we want 80% of those values or records to be saved in what is called a trained data set. So 80% of this data set, which is the X data set, 80% of the records, we will save them in X train. That's the variable that you see there. Then the 20% that will be remaining, we'll save it in X test. Then on this other side, for the test, for the target variable, the one that we've saved in Y, 80% will be in X test and 20% will be in Y test. The reason is because we've splitted actually our data set into 4, but technically it's actually into 2, into what is called a training set and a test set. The training set has features which are 80% of the original one, and it also has target values which has 80% of the original one. So we have X train and we also have Y train. So these are the training. So we're going to use our model and we're going to get our model and train it off the X train and Y train. And then later, once we've trained the model, we are going to ask the model to predict the values of X test. These are the features to predict its own values of target values. So it's going to predict target values for X test, and then we will get those, predicted values by the model and compare them with now the y-test. You can rewind the video, by the way, if you realize that I've lost you there. So we get a model, we train it off X train and Y train, and later, once it's been trained, we say that we would want that this model to predict X test, and then it predicts its own values, but we take those values and we compare it with Y test, which were the actually original values. And that's how we are going to know how our model performed. If the values are closer to what was in Y test, then it means our model performed well. There are various metrics that we can use. There's what is called accuracy metric. It can tell us, like, out of all these records, it predicted 90% correctly, and we can say, okay, we are confident, and we can use that model for that purpose. So that's what we do here. We are splitting our features and target data set into X train and X test. Same case with Y train. The same case and that's what we are doing. We are splitting them into X train, X test, Y train, and Y test. So 4 different data sets, or you can think of them 4 different variables. And we use the train test split function from sklearn, and from actually specifically the model selection module. And we give the train test split function this X variable and Y. These are the 2 data sets that we had initially separated, and we defined the 20% using the test size. So we say 0.2, which is 20%. It's 2.5, that's 25%. 3, 30%. Normally the test size is usually smaller, so we want to have a smaller test set. So that's what we want the values here to be smaller, so that we can use them to make our prediction. But sometimes you can do comparisons. You can create a model, then you can create multiple models, like a first set of models with a test size of 0.2, then compare that with what if you had with models which had 0.3, and then you make that prediction. Random state 42 just means that the way you have split your records, like if a record was put for X train, in any case where you are running this code, that record will still remain in X train, all those records. The same case, it just makes also other people be able to reproduce your results. Otherwise, if you don't put random states and set it to 42 or any other number, it could be 0, it could be 10, then they'll always get different results, because here the X train values are different. So random state, you always just ensure that you can put 42, you can put 0, but ensure that when you're giving those other people, they also don't change random state. It's also like that. And then we now import our machine learning algorithms for specifically classification. There's logistic regression, Gaussian naive Bayes, there's KNN, K nearest neighbors, there's decision tree, there's random forest. These algorithms, we can cover them separately in a different workshop on, let's say, on classification analysis. Just note that they work differently, and in some situations they also have different assumptions. Like, one of them, such as logistic regression, would need to ensure that the values or the variables that you have in your feature set are not highly correlated. So weight and height should not be highly correlated. Otherwise, you would need to ensure that you drop one of them, or you transform one of them so that they are not correlated. So there are those assumptions that you might want to work towards, but sometimes I usually feel it's important to just work towards, not even feel, I usually find that it's important to work towards that aspect of now checking for assumptions if it turns out to be the best performing model. So you would want now to further optimize it. So you check for assumptions, you check for maybe it assumes that you would have lots of features, so you would go for that, etc. So we import those models, then we instantiate them. So once you import a model, you'd want to create the model. So we've imported them, but we haven't worked with them, so we get to create with them. For K nearest neighbors, we normally specify this parameter, the neighbors, like how many of the records that it gets to learn from should determine it's how it predicts. So how it works would also be dependent on this number. So you need to set that. And then we train our model. We train each and every model. So we have 5 different models. We use the fit method to train. We use the X train and Y train that we had here. And then once we have done that, we evaluate how the models perform by predicting the X test. Remember when I was saying we need to predict X test? And then once we have done that, so we are predicting we're predicting values for X test, which we will later compare with Y test. Once we have made those predictions, we then calculate the accuracy scores in comparison to Y test. So we will predict those predictions for logistic regression. We save them here, and then we use the accuracy score function to calculate that accuracy score. And then we print those accuracy score values. So let me just run the split train and train model code that has run. We instantiate and train the model. Put an N here, but it's okay. It's still going to work. Don't worry about this output. It's because we have this as the last one. Then we evaluate by predicting the new values of X test, and we compare with the original Y test, and we get our accuracy on a scale of 0 to 1, how the model performed. So generally, these are the accuracy scores. We can use other evaluation metrics, but these are just the most common evaluation metric. This is the most common evaluation metric when it comes to working with classification models. So these models actually perform really well, but again, it's also dependent on a metric of success. Like a stakeholder might tell you that we want the best performing model that surpasses 95% of its predictions. So that has an accuracy score of 95% of 0.95. Then you can go for either of these ones, and you can further now see how you can optimize these two by simply understanding whether the assumptions that it takes into account, let's say naive Bayes or k nearest neighbors, take into account. So, or even performing what is called feature engineering, like looking for more data or from existing data, like the way we did with blood pressure. We split those 2 columns to create a new 2 columns, etc. Then we make new predictions. So here we are going to create some new data set, that some new record that has information about a new patient, and we want to predict how the new patient, we want to predict a new column. So what we want to predict would be actually, let me just run this. This is the new patient data, and we want to predict the heart, whether they have heart disease or not. So we use logistic model. We use a predict function and new data. So this is the new data, and we make those predictions, and all of them say 1, which 1, as we had remembered here, heart disease means that the patient will have heart disease, and you can now automate that process, by the way. So yeah, so that's for classification. Extensive process. You can study it closely, you can pause the video, and then go over that, and yeah, work on the challenge. We provided a challenge question, research question, that allows you to just work with just one model. We've provided just some pre-code so that you only focus on the machine learning part. So you can use the example to work on the challenge. Pause the video, and then once you're done, we can continue. If you're an Afterwork member, we have a solution, but I can even just display the solution for this one. So this is what you might be expected to have. You can pause also this video. All right, moving on. Regression. So for regression, remember for regression, we are predicting a numerical variable. So let me run this. The problem that we are trying to solve is how do different regression models performing when predicting a patient's medical cost. So our variable of interest is medical cost. So we import the data set. We can describe it just and have an understanding of it. And then once we have done that, it's taking a bit of some time. Let's just see how much time it takes. Okay, so we have been able to display the statistical summary. We can see there are no missing values. So yeah, we can still go ahead and do the pre-processing steps like what we did, convert the categorical variables to their numerical equivalents, etc., and drop patient ID. So we do that for gender, blood pressure, insurance coverage, and also drop these two columns, and also drop missing values, and print out the resulting data set, which we have here. And then we later onwards, this is a new method. Instead of selecting the individual columns, we can decide to have the features, get the values for the features differently by simply dropping the medication cost from this data frame, so that we are left with the remaining ones. So then those are the ones that we store in X. Same case for, we just refer to medical cost and we save it into Y. Here we are now also doing something else that is called this is min-max scalar, that is called standardization. So what we are doing here, we are converting all the values here to have values which are between 0 and 1, so that values of one variable such as weight do not affect how our model performs, so that they are treated the same as, let's say, other smaller values like insurance coverage or maybe gender. So yeah, so that's what we are doing here. The data sets that we get to work with here, and then we can, this is what this was supposed to have come here, X test normalized Y. I'll update that in the original notebook, realize that. Okay, so I think the problem should be these ones haven't been initialized. I'll have to do this here afterwards. I would have to convert those values, do this text preprocessing step a bit later. So this is Y, this is Y. So I would use this to, I can still say X train and X test later. I think that's okay. Yeah, so if I run this, it should work. And then I import our models, then I instantiate them, then I train them, then I calculate the accuracy scores. So for regression, we don't use accuracy score, we use other metrics. For regression, there are metrics for that. There are classification models, there are different types of metrics. For regression, or the common metric is usually called root mean square error, which usually comes from 0 and it goes up in terms of values, and the closer a value is to 0 means that you are having a good model. So if we run this, we are going to be calculating the root mean square error. So if I calculate this, I should be able to get root mean square error. It's like for 2, the one that you see has 2, which is closer to 0, it means the model performance for that is actually better than the one that has 26. So these are the models that we've imported. Linear regression decision tree, this linear regression decision tree, support vector machine, random forest model, as well as gradient boosting regressor. And then we make predictions for that. All right. You might get some error, but don't worry about this one. All right. At this particular point, pause the video and then work on the challenge. Moving on, clustering. For clustering, it's almost like what we had mentioned, only that we are trying to make predictions. So let's load this data set. So we are training we're telling our model to uncover findings. So we pre-process the data, we normalize the data before, and then we pass this data to our model, and we tell it that we want to group the data into 3 clusters. and then we evaluate the we get the new column. So new columns as a cluster, which are the clusters 0, 1, and 2, and then we can check for the optimal number of k, which is the one that we have here, 3, which is now 2, and 2 because of the elbow, and then we can change that, and then we can preview the clusters. And that's it for this workshop. All the